Welcome to Homework Lib.
In this problem, we are considering a potassium chloride molecule. So we have a potassium and a chlorine atom, and they're bound together with some energy. Be is what I've called it here, but that's just the binding energy of the molecule. And the problem wants us to use all the data that we know about this molecule to estimate the equilibrium separation, so the distance between the two, r, between these two atoms. And the way that we should consider to approach this is to think about what we know that relates distance to energy. And in this case, the most obvious thing is the Coulomb potential, where you have Q1, Q2 all on R, which we already had a problem earlier in the chapter about this, but this is the only conceivable way we can figure out this distance. So the process for working this all out is we need to get a relationship for the um, potential energy. And how we can figure that out is by knowing that the binding energy is going to be equal to the potential energy written as a positive minus the energy cost, which I will write like this. The energy cost of bringing this molecule together. So let's look at this first. The energy cost is simply the ionization energy, so how much energy it costs to rip an electron away from potassium, minus the electron affinity, so how much uh, the chlorine atom really wants to take on an electron. So we have the values here. They were given in the text, and that is just 0.7 eV. What we can think about this value is how much it costs to remove an electron from our potassium and give it to the chlorine, because it actually takes a little bit of energy to rip it away from the potassium, and it's balanced out by the energy hole that the chlorine has. All right. And the binding energy is given as well, because this is something also from the text and that can be measured in certain ways. So we have an energy cost and a binding energy. Let's rearrange this equation to get a function for u is what I switched to calling it here. Let's replace this v with a u to be consistent. So u is going to be equal to binding energy plus the energy cost, which we calculated just now. And if you turn the crank on this, you get that our potential energy is 5.13 electron volts. All right, well, that is good, except we don't really just want the potential. We want to work backwards and get this R. So we plug in for here, and we have 5.13 eV is equal to Coulomb's constant, which is 1 over 4 pi epsilon naught, times Q1, Q2, all over R. Now, in this case, Q1 and Q2 are the same. They're just the elementary electric charge. So one of them would be negative, but the notation in this book takes binding energy to be a positive. So we're going to leave it just as the magnitude of the charges. So you get K E squared over R. And then we want to shuffle things around a little bit because we're trying to calculate R, which we get 5.13 over Ke squared. And if you do the calculation here, you see that the oh, sorry, no, this is backwards. It's Ke squared over the binding energy. I got too fast. But regardless, if you do this calculation, you see that the distance is 0.287 nanometers. And that fulfills the calculation part of the question. However, it also asks to explain why this result is only an estimate and not a precise value. And the key assumptions that we've made here, one is that we assumed both of these are point charges, which is not necessarily the case. They do have some charge distribution, but we've also assumed that there's no energy coming in from kinetic energy, which would change the binding energy. It would lower the binding energy a little bit. So we actually might expect the binding energy to have this influence from the kinetic energy, thus giving us a little bit of a wrong calculation for the distance between the two.